Before we get started, if you haven't subscribed to the channel, please consider subscribing.
We are going to estimate the returns to education following Angrist and Krueger's 1991 QJE paper, Does Compulsory School Attendance Affect Schooling and Earnings? You can take a look at the original paper here, and if you look up in QJE website for this paper, and you can also download the paper and read through the whole paper and see what kind of analysis they did. But the main objective of this video is to replicate some of the results in R using the dataset that they've made available on Angrist's website here. And then we'll compare a few different methods, and we'll also look at how to nicely represent data in results that are done in R, and then like how to make a nice table where we can compare the results of different models and then generate publication quality outputs from these. Okay, so let's start with first where we can find the data. So the data is available on Angrist's page in MIT's website. You can see he has made data available for all the different papers that he has worked on. So we'll just go to Angrist and Krueger 1991, and the dataset that we'll be working with is this new 7080.rar, which includes the Stata file with the original 1970 and 1980 census data, which includes all cohorts and covariates. So I have already downloaded the data and I have it in my local drive. And let's take a look at the key items that we'll be working with. So the first section of this problem here is basically setting up the data, clearing the variables, giving the variables some variable names, getting all those things ready. So that's not important here. The important things are basically how to run the models and how to summarize them. And so let's look at this. This is asking us what is the estimated return to education and its homoscedastic standard errors. And it's giving us a bunch of instructions on how to do this. And then the next thing is reporting the 95% confidence interval for the return to education. So we'll see how to do that in R, and then we'll see how to do quantile regression in R using the function RQ, and we'll run it for different quantiles. And then we will report the coefficients as well, and then the whole idea is to be able to replicate the results and then display it in a nice format so that we can compare the results. So let's get started with the code. So the first thing is we'll be using the library foreign. We can use this library to read status.dta files in R. So as you can see, the new 7080 data is in .dta format. So we first read the data, and we can take a look at the variables, and we can see that the variables are not well named. So the first thing we do is we rename the variables. And you can download all of these scripts and all the data sets from my website's resources, which I'll make available, and I'll also give a link in the description. So once we have renamed, so I'll not go through the tedious parts because you can just look through them yourself or pause the video. So the next step is we select the observations. So again, we are in the tedious part of the process where we clean the data, we organize the data. So we're basically subsetting. We focus on middle age to men in 1980 for this exercise. So we are keeping census 1980, and then we're keeping age greater than equals to 40 and age less than equals to 49. So the selected individuals were all between the ages 40 and 49 at the time of census. Therefore, they are expected to be finished with their education or studies and still too young to retire. We need to get two variables, age and age squared. So HQ is a variable that is present in the dataset that gives a more precise age by incorporating the quarter of the birth. And we need to remove 1900 from HQ. So we create this new variable HQ, which is HQ minus 1900. And then we create HQ squared, which is basically the old variable raised to the power 2. And here we can look at some of the results from our HQ variable here, some of the data. All right, after we are done, we can save the data frame for future use since we've already cleaned and renamed the variables. So here is the main estimation of the returns to education. So the first step is I want the output to display nicely and not have very long numbers. So I'm going to force R to display using the scientific option, scientific display, but limit it to only 4 digits. And estimating the returns to education using OLS. So this is the model. We can go back to the problem that we were attempting to solve, and see if we have. And here we can see we have the basic model. The main equation of interest, which is sometimes called the Mincer equation, is given by the log of weekly wage equals to beta times years of education plus a bunch of covariates. And these covariates include race, marital status, geographic location, age. So the best idea would be to go back to the original paper and see what variables that they had kept in their analysis so that we can replicate them. So the formula that we're using is log of weekly wage is equals to education plus race plus married or unmarried dummy, SMSA plus new ing. So these are, I believe, the different regions and the dummy variables for those regions. And then we have age and age square and year of birth as well. We're using it as a factor so that it as factor basically tells R that we want to treat it as a continuous variable instead of strings. And lm is the main command, which is linear model or basic OLS. So this is basically the usual OLS with homoscedastic errors, and this is the result. I'm not going to go deeper into the results because the purpose of this video is to see how to implement these kinds of models and display the results. So the estimated return to education is 0.0634. Again, you can see the code that I've used paste, and then I'm basically joining two different parts. The first part is the string, and the second part is the data that we have that we've generated by running the model, and it's coefficient number 2 column 1, so row 2 column 1, right? So row 2 and column 1 is the estimate. If I had put in column 2, it'll give me the standard error. If I put in column 3, it'll give me the t value. So that's how it works, and then I'm rounding it up to 4 digits for a better display. And again, you can see I've used column 2, row 2, column 2. So row 2 is education, and then column 2 is standard error 0.00340, and that is exactly what it displays. And now we want to report a 95% confidence interval, and the easier command to get this is conf int. This is the command that we use in R, and here we can see this is 2.1 and this is 2.2. So again, this is telling R to fetch the confidence interval column 1 and column 2, so basically the lower bound and the upper bound of the intervals. And finally, here is the quantile regression. We're using the library quantreg, and that library basically contains the quantile regression command. And the command is simple, rq, just like lm, very simple. We have the same model in here. The only thing different is we are now telling it the tau values, which is basically the quantiles that we want to estimate at. In this case, it's 5%, and then the second model here is 50%, and the models are also named accordingly so that we can understand too. And the rest of the things are basically more default settings. And here is the 95th quantile as well. Okay, and lastly, we are using model summary library to report the results in a clean way. All right. Here are some warnings. We can just avoid them, or we can also set up display warnings to false at the beginning of the markdown document, which I didn't do here. So first is we make a list of all of the 4 models. So list, and then we give a name to each of the model in strings. So this is the string OLS, which is assigning the first model that we did, the OLS model. This is a string naming the quantile regression at 5%, and it is assigning the second model, which is the quantile regression at 5%, this model, to that string. So likewise, we basically name each of the different models, and then we are putting them together as a list. And now we report a table with the results focusing on the estimates of education. So we use the model summary command, which is basically coming from this model summary library. And our list is named all models. So all models, so this is bringing the list. We want to omit the stars, so we basically use this argument here, gof_omit. We want to display the statistics as the confidence intervals, the standard errors, the t-statistic, and then the p-value. And then we only want to keep the coefficients of education and not show others, right? So, all right, so here we can see SE is represented like S.E, the way we have assigned it to, T is represented like T, P is represented by P. So the first sections here are basically how we want to write them out, and then the second sections are basically the statistics that it's going to pull from the models that we have saved in this list. All right, we can see the estimate of education from OLS is 0.06. From the quantile regression at the 5% is again 0.065 or 0.07. At 50% it's 0.06 again. At 95% it's 0.07. So quick takeaway, those who are at the 95th percentile of the distribution are getting a higher returns from education from those who are at the 50th percentile. But again, those who are at the 5th percentile, so at the lower end of the distribution, those folks are getting a higher return from those folks who are at the middle. And this is sort of like an average, for the average person, what's the estimate? That's the OLS one. And then we can look at the distribution, and we can see that the distribution of log of weekly wage given the education and other characteristics. Of course, keeping in mind, we are only displaying education, but this is controlling for all the other variables as well that we have modeled in these analysis. So, if you like my videos and find them helpful, then please support my work by subscribing to the channel.